When you picture gold mining, you probably imagine someone panning for shiny nuggets in a river. But modern gold extraction looks more like this industrial rock crusher. To get to today's gold, we have to pulverize large boulders into a fine, uniform dust just to isolate microscopic trace amounts of the precious metal. This diagram shows the next step, a process called cyanidation. Instead of sifting through dirt, miners submerge that rock dust into a chemical bath. The solvent aggressively attacks the ore, forcing those microscopic gold flecks embedded inside the gray rock to dissolve outward into a brightly colored liquid solution. To collect that dissolved gold, traditional operations use a method like zinc substitution. This method has a strict physical requirement. As you can see here, the mixture must pass through a fine filter membrane. The solid rock dust is blocked, and only a perfectly clear liquid gold solution makes it out the other side. For decades, the industry operated on the assumption that solid rock dust and liquid gold could be separated by a physical filter. But certain geological deposits defy that assumption. High oxide ores don't crush into a clean, uniform dust. Instead, they turn into a thick, heavy, viscous mud, known in the industry as pulp or sludge. Looking at this technical schematic, we see the physical bottleneck. When this heavy sludge hits a traditional filter, the fine membranes instantly jam. The flow of liquid stops, and internal pressure rapidly builds. The gold has been successfully dissolved, but because the mud is too thick to pass through a membrane, those millions of dollars in dissolved metal remain trapped in the sludge. Extracting wealth from high oxide ore requires a different approach to engineering, one that bypasses the filter entirely. The solution is the Carbon-in-Pulp, or CIP process. Rather than trying to force the liquid out of the mud, engineers drop a collection medium directly into the sludge. This medium is activated carbon. Thanks to its highly porous surface, activated carbon has a unique chemical characteristic. It attracts and holds onto dissolved precious metals. Before the carbon goes in, the raw ore requires preparation. The rock is ground down until it passes through a 28-mesh screen. Wood chips and impurities are stripped away, and the mixture is diluted with water until it forms a precise 45 to 50% concentration slurry. This diagram illustrates the next stage. That precisely mixed slurry is pumped through a series of 5 to 8 massive industrial stirred tanks. Inside, the cyanide continues its work, ensuring the gold fully dissolves. At this point, the gold exists in a liquid state while the thick sludge remains intact. The physical extraction of that liquid can now begin. Now, the highly porous activated carbon is mechanically dropped directly into these massive stirred tanks, right alongside the dense sludge. In this tank cross-section, engineers use reverse flow. The muddy slurry flows right to left, while black carbon pellets move the opposite direction. Zooming in, the carbon pulls dissolved gold out of the mud, bonding tightly to the pellets. A mechanical risk is gold-loaded carbon washing out with the mud. To solve this, bridge screens at tank exits trap the carbon pellets. Bursts of compressed air blast across the screens, preventing clogs and allowing only barren mud through. Through this precise mechanical choreography, the gold is separated from the sludge, without a single drop of liquid ever passing through a traditional filter. The gold is out of the mud, but it is now chemically trapped inside solid chunks of carbon. In this pressurized chamber, we see the desorption process. Operators flood the loaded carbon with caustic sodium cyanide, applying extreme heat. This environment breaks the chemical bond, releasing the gold back into a clear liquid state. This reaction yields a highly concentrated, high-grade liquid gold solution, now separated from both the mud and the carbon. In this illustration, we see the final step. Facilities use either electrowinning or a zinc replacement method to precipitate this clear liquid into raw gold powder, which is then dried and sent for smelting. The physical extraction of solid gold from unfilterable mud is finished. However, the operation is unprofitable if it stops here. Activated carbon is expensive. To make the math of the CIP process work, the facility must reuse the exact same carbon pellets thousands of times. Once the gold is removed, the bare carbon is washed with dilute sulfuric acid to strip away accumulated carbonate scale and other microscopic impurities. This macro flowchart outlines the final step, thermal reactivation. The cleaned carbon passes through a heat kiln to restore its porous adsorption properties. Recharged, it drops back into the initial slurry tank to catch more gold. By mastering this closed loop, CIP technology salvaged mining sites around the world. Deposits that were once considered waste because of their high mud content became profitable sources of gold. The carbon-in-pulp process bypassed the physical bottleneck of filtration by changing where the collection happens. By removing the need for a filter, it turned high oxide sludge from a waste product into a primary source of global gold production.